What's going on, everybody? We are moving to a new chapter and a new subject here. We're moving on from rational expressions to radical expressions. A radical expression can be summed up as any kind of algebraic expression. Maybe there's some variables in there, maybe not, but have that familiar square root symbol that you might recall learning at some point. You'll have a square root sign in there. This could be a cube root, a fourth root, a fifth root. As it turns out, there are an infinitely high number of roots that you can use. How do we simplify these things? How do we work with these things? How do we solve equations that have them? How do we graph these things? This is the focus of this unit that we're now in right now, and we're going to introduce you to this new world of radical expressions here. But before we do that, let's take some time to focus on our breathing and empty our thoughts for a little bit. This is a good thing to be doing in this time. I know that everyone is at home. I know that you're probably very bored being surrounded by Netflix queues and YouTube videos and things like that. We surround ourselves with so much content. It's so good to turn everything off, not just outside, but also on the inside. I find that if I've been surrounded by content for a long period of time, it's really, really hard to do this. But I would strongly encourage you to take the time to move beyond thought and into awareness, to get in touch with that piece of stillness that's inside of you underneath all of the chaff that's rolling around in form of all these random thoughts that we sometimes struggle with and which get in the way of learning. So let's take some time here to focus on your breathing, to empty your thoughts, and to become ready for what it is we're going to be talking about today. Welcome back. Well, let's start with the square root of 25, and you might be surprised at the language that I use here, in which I say find all square roots of 25. All square roots of 25. Isn't there just one? 5 times 5 being 25, so the square root of 25 should be just 5. More specifically, the question that we ask with square roots is, what number do I square to get 25? And you might be thinking, yes, of course, 5 squared is 25. What number multiplied by itself is 25? That's another way of saying it. It is true that 5 is an answer, but it's also true that negative 5 is an answer here. The negative times a negative is a positive. Negative 5 times negative 5, that's also equal to 25. And so we can actually describe this in two different ways here. When we're describing what the square root is, there's two possible solutions, and we want to be a little bit more specific when we're describing a square root here. So the default value here for the square root, what we call the principal square root here, is the positive square root. So square root of 25, when you just see it like this, that's positive 5. We'll also sometimes show you this, in which there's a negative sign sitting outside the square root, in which we're specifically referring to the negative square root, which would be negative 5 in this case. And so just some terminology that's associated. The word radical might be, at least in the context of mathematics, might be new to you. Basically, a radical is whenever you see this kind of a sign somewhere in a algebraic expression. Somebody might point to the top of a fraction and say, that radical up there, and they're referring specifically to the portion of the algebraic expression that's got this term above it. The actual symbol itself is called the radical sign. You might think of it as the square root symbol. It's more generally known as the radical sign. And the item that's inside the radical sign is called the radicand. In this case, it's 25. Once again, we have two possibilities here for the square root. The positive square root we sometimes call the principal square root, and as you can see, it's just represented here with the square root of 25 without any minus sign out front. We also have the negative square root, which is symbolized with the negative sign in front of it. So how would we find these square roots? And we say, if possible. Believe it or not, there are some instances in which it's not possible. Let's think of what some of those things are as we're going along with this. The principal square root of 100, that's 10, that makes sense. The negative square root of 16, well, 4 times 4 equals 16. It's also true that negative 4 times negative 4 is 16. So we're specifically referring here to the negative square root of 16, which is negative 4. Now think about how we deal with fractions when we're working with square roots here. What this is specifically asking is, what number times itself will give you 425? Well, let's think about how fractions multiply. How do fractions multiply? You have a fraction here, you have another fraction here. The way that fractions multiply is to multiply tops and then also multiply bottoms. So let's just focus on the tops here. What number multiplied by itself gives you 4? Well, the answer is 2. And what number multiplied by itself gives you 25? The answer is 5. So in the case of a fraction, you can actually take this square root and think of it as this, square root of the top and the square root of the bottom here, at least in finding out what the principal square root here is. In this case, we've got our answer of 2/5 here. In this case, we're doing something very similar, but it's going to be a negative square root. This is going to be negative 9/7. And then lastly, we're faced with this one here. In these two problems, the negative signs were outside the radical. Now the negative sign is inside the radical, and so we're asked the question, what number multiplied by itself gives you a negative 9? Well, you might say negative 3, but a negative 3 times negative 3, that's positive 9. As it turns out, there are no real numbers that, when multiplied by themselves, will give you a negative answer here. And so the answer here is not a real number. And when I say real number here, that's actually an indication that we'll be moving on soon to what are called complex numbers, which include a branch of numbers which quite inappropriately are referred to as imaginary numbers. They were actually originally called lateral numbers, which I think is a better term for them. But right now we're dealing with the real number system, and for a real number system there is no answer to this kind of a square root. So take some time to do these here as well. These are some additional problems for you to work out. Take some time for that. Welcome back. Well, this provided some pretty solid reinforcement on what we were doing beforehand. The positive and negative square roots, the principal square root, the negative square root was represented here. We took the same thing with some fractions, 5/6 and -1/8, and we got an example here of trying to take the square root of a negative number, which is, as before described, not a real number. Let's actually talk about that a little bit more here. The square root of a negative number, as it turns out, there's no real solution to that. Let's actually explore that in a little bit more detail here. I've got a number line here extending, this is 0 in the center here, extending negative numbers to the left, positive numbers to the right here. And as we were describing prior to this, there really is no for any radicand that is a negative number, there is no square root that is a real number. And so an example here, the square root of -4, even though you might be thinking 4, the square root of 4 is +2 or -2, the square root of -4 is not a real number because -4 is less than 0. There's a second case here in which we are at least non-negative. We could be 0 or positive, and the radicand is a perfect square, like 1, like 0, 4, 9, 16, 36, 100, and so on. In which case, when you take the square root, you get what's called a rational number. And remember, we've been talking about what rational numbers are. When you think of the word rational, think of the smaller word ration, or even the smaller word ratio. You can describe this in terms of two whole numbers, one on top, one on bottom, as a ratio of those two numbers, as a fraction of two, in which there's a whole number on top and a whole number on bottom. You can certainly do that with 9, with 4, with 1, 4 to 1. That's a pretty easy ratio there, 9 to 1, and so on. And so these are numbers that are rational numbers, and so we can describe any one of these square roots as a rational number. If the radicand is not a perfect square, and it's positive, then what we get is actually an irrational number here. What is an irrational number? Well, as it turns out, there is no way to describe the square root of 7 in terms of a ratio of two whole numbers, as a fraction that involves just whole numbers, top and bottom. There's no way to describe that, believe it or not. So for all the square roots that are in which the radicand is not a perfect square, this is true. You might have heard of some irrational numbers prior to this. Pi is a good example. The one property of the irrational number is that it is an endless decimal that repeats without any pattern. That's also true for all of these square roots that are rational as well. So pi, e, the golden ratio, a lot of these things are just irrational numbers. They're pretty amazing numbers in that case. They have infinite complexity in which to describe them. So they're interesting to me, at least in that regard. Okay, and as it turns out, we don't just have square roots to talk about here. That's what this symbol here is, in which we ask what number times itself is equal to a. We can also ask the question, what number times itself is equal to a? And that's the cube root of a. What number times itself is equal to a? That's the fourth root of a. And what number times itself is equal to a? That's the fifth root of a. So we can describe these things, and just to keep in mind, here's what the terminology is. Square root of a, when we took a number and multiplied it by itself, a shorthand way of saying that was squaring. So when we're describing two numbers that could multiply to get a, we can describe that as the square root of a. When we're taking a number times itself, we are cubing that number. So the opposite of that, so to speak, would be the cube root of a. From there on, we just use the numbers, the fourth root of a, the fifth root of a, and so on and so forth to describe these things. So let's find some of these higher roots that we have here. Find each root. So the third root of 125. So what number times itself equals 125? Well, the answer to that is 5. Since 5 times 5 times 5 is 125, 5 times 5 is 25, and 5 quarters is a buck 25, 25 times 5 is 125. So the cube root of 125 is just 5. And what number do I raise to the fifth power here to get 32? So that's the question behind the fifth root of 32. As it turns out, 2 times 2 times 2 times 2 times 2 is 32. You can figure that one out for yourself there if you want. But if that's the case, then the fifth root of 32 is just 2. So take some time to find these roots as well, the cube root of 27 and the cube root of 8. Take some time for that. Welcome back. Well, perhaps you're noticing that there's a little bit of extra thought that needs to go in when you're figuring out a cube root. That's not something that we tend to have a whole lot of practice with here. We have to start thinking, okay, well, what number multiplied by itself gives me this number. That takes a little bit of extra time and practice here, but hopefully that was straightforward enough. The cube root of 27 being 3 and the cube root of 8 being 2. Now there's something I also want to introduce to you here. Remember when we were talking about how the square root of something, the radicand always has to be non-negative. We can't have negative numbers inside of here. That's true for the square root. But let me ask you something here. What happens if I try to take the cube root of negative 27? Is there a solution for that? So once again, what number do I cube to get negative 27? Is it possible that negative 3 cubed would be negative 27? Let's check this out here. That's negative 3 times negative 3, times negative 3 here. Negative 3 times negative 3, the negative times a negative is a positive 9, times a negative 3, well, a positive times a negative, that's a negative. Interesting. So in this case, I can get a negative value here when I take this when I take this number here and I cube it. So in this case, the cube root of negative 27 is equal to negative 3. And in the same way here, what's the cube root of negative 8? Well, you might be guessing that it's negative 2. Let's check that out. Negative 2 to the third power, that's negative 2 times negative 2 times negative 2. Negative 2 times negative 2, that's positive 4 times negative 2. Yep, it's negative 8 here. So the cube root of negative 8 is going to be -2. What's the difference between this and the square root? The difference is that this number here is odd instead of even. If we go back to the fourth root of, say, 16, now we're back to this number having to be non-negative. It can be 0, it can be positive, but it can't be a negative number. But if we go to the fifth root of -32, that's okay, because this power here is, this root here is odd instead of even. So interestingly enough, we have a set of rules here for defining in general, the nth root of a. So we're describing in general terms here, what is the properties here of these particular roots here. And as it turns out, the first thing we have to ask here is the variable n even or odd? And for square root, we consider it as being a 2, so that's even. And so when it's even, it has its own rules here. But if it's odd, then there is one real nth root of a, regardless of whether or not a is positive, negative, or 0. We know that we're just going to get one real nth root. That's if n is odd. What if n's even? Well, then we have to ask the question whether or not a is positive or negative, or 0, I really should be saying. And if it's negative, then the answer is there's no real nth root for this, for a here. And for positive, or, I'm going to write here, or 0, the answer then is the principal nth root of a is the nth root of a, the negative nth root of a is the negative nth root of a. So we have this duality here. This is what we were talking about beforehand, where the principal square root of 25 was equal to 5, but the negative square root of 25 is equal to -5. So it's possible for there to be two solutions, either two solutions or no solutions, when you have the variable, when you have the root, the root here being even. So let's find each root if possible as we go across here. You can see there are negative signs in different locations. There are even roots, odd roots. Let's see if we can figure this out here. The fourth root of 16. So what number times itself times itself times itself is positive 16? The answer is 2. And we also, since this is an even root here, we have a negative possible solution as well. This is just going to be -2. So the negative fourth root rather of 16 will be -2. But the fourth root of -16, what number times itself times itself times itself is -16? There is no real solution to that, none whatsoever. But now let's switch to cube roots here. Now the root is odd, so now no matter what, we're going to get a single solution, one solution, and there's always going to be a solution no matter what. Well, what number times itself is 64? You might be surprised to find that that's 4. 4 times 4 is 16. 16 times 4 is 64. So 64 is kind of an interesting number in that it's a perfect square as well as a perfect cube. That's what makes it kind of a cool number. So the cube root of 64 is 4, and the cube root of -64 is -4. We can do that because the root here is odd. So take some time to do these as well for some additional practice. Welcome back. Well, this is good practice and the different rules that we find when we're dealing with uh, even roots as well as odd roots, as well as the different rules that come into play when we've got negative radicands as well as positive radicands. Now, there's something I want you to see here that might be of some value to you as well. You can think of 64 as being 2 to the 6th power. And so what's interesting about this is that we kind of saw the exponent here of 6 and the 6th root of here. These two things sort of canceled out, didn't they? And so we went from 2 to the 6th power, 2 being raised to the 6th power up to 64, then being taken the 6th root of that. Well, now we're back down to 2. In the same way here, we can describe this as the negative 6th root of 2 to the 6 here. We had 2 being raised to the 6th power up to 64, and then we take the 6th root of that. It's back down to 2. Oh, and it has to be the negative solution for that, so negative 2. For this one, it's no real solution, but for this one, we can describe this as the cube root of 5 cubed. So once again, we see an instance of the exponent and the root canceling each other out when they're the same like this. And we also have this instance over here of negative 5 being raised to the 3rd power here. Make sure that when you're raising a negative number to a power that you have to place that negative number inside parentheses here. So negative 5 being raised to the 3rd power here, and then having the cube root taken of that, we're back now to negative 5. So it almost looks like the exponent and the root, if they're the same number, they're just going to cancel each other out. Turns out that's almost true. We can see an instance here for the cube root. Let's actually take a look at this one to the right here first. Negative 4 raised to the 3rd power, negative 4 cubed. Then we take the cube root of that. That's going to be the cube root of negative 64. And so we do, in fact, see an instance in here in which it looks like the exponent and the root just cancel each other out. That's true here. But watch what happens here with this square root and this squared. We start off with negative 3 here. We square it, it becomes positive 9. And when we take the principal square root of 9, it becomes positive 3. So we go from something that's negative to something that's positive. And that's because whenever we're taking the principal square root of something, the answer always has to be positive. So for odd roots, yeah, these things cancel each other out. For even roots, the answer is always positive. And what's our symbol for making it so an answer is always positive? Let's think about what that is in a second here. So the answer here is that when the root here is even, and the exponent is even, in fact, if it's got to be the same number here, then when we take the nth root of a to the n, that's not just a, it's the absolute value of a. It has to be positive. If the variable n is odd, you're taking the odd root of the nth root of a to the n, then yeah, things just cancel out and you're left with just a. So let's use that here for these particular examples here. Here I'm dealing with an even root and an even exponent here. It's this is squared and this is a square root, so yeah, we can think of this in terms of sort of canceling, but since it's even, the answer has to be the absolute value of negative 7 or just positive 7. Now for here, it's a variable. We don't know if k is positive or negative, so we have to leave it as an expression. And again here, this is the square root of something squared. It's an even power and an even root, so we have to just express it saying the absolute value of k and just leave it at that. This one's an odd root taken of an odd exponent, 3 and 3, so yeah, things just cancel each other out. Same thing here for when it's a variable. Here it's even again, and so this has to be the absolute value of y minus 9. And lastly here, this is an odd pair here of root and exponent. So this just reduces to 8p plus 1. So here's an example of another 6 problems, very much like those. Take some time for them. Welcome back. Well, we're starting to see how some of these radical expressions behave and how they interact with exponents here. You can see that since we're dealing with a square root and a square here, they don't fully cancel each other out. We have to deal with an absolute value of -12, which is 12. Same thing here, and same thing down here, dealing with even roots and exponents. With this one, with this one, and with this one, we're dealing with odd roots and exponents, and so the cancellation is perfect, just leaving behind what was in the radicand underneath the exponent. Since we're starting to see how these things behave, we can start to talk about square root and cube root functions. These are functions that involve, well, square roots and cube roots here. So an expression that contains a radical is called, well, creatively enough, a radical expression. So that's one that's similar to what we were seeing before, the square root of 2t plus 1. That would be a radical expression. Radical functions are functions of this form here. So if we have f of x is equal to the nth root of x, so this is functional notation here that's placed on one side of the equation with a radical expression on the other side here. This is a radical function. Two examples of some square root functions might be this being the simplest one, and here another one, we're defining a function g with a variable with an independent variable of r. It's the square root of 2r minus 9. So that is another example of a square root function involving a radical expression. So let's see how we work with these square root and cube root functions here. Let's just start with square root functions, where f of x is equal to the square root of x. So for f of 64, we're just plugging in 64 into this expression here. Replacing x with 64, that becomes the square root of 64, which is just 8. So f of 64 is 8. We're going to switch here to g of 7. So we're replacing r here with 7 in this expression. So g of 7 is equal to the square root of 2 times 7 minus 9. Order of operations says let's do multiplication first. 14 minus 9, that's the square root of 5. 5 isn't a perfect square, so we have to leave it just like that, square root of 5. Now we can describe it as a decimal here, but the most exact way of describing it is just here, just a square root of 5. Let's do this. Let's plug -25 in to f of x. We're replacing the x here with -25, so we have the square root of -25, which, as we've seen from before, is not a real number. So as we're going to start talking about soon, -25 is not part of the domain of this function, nor any of the non-positive numbers, nor any of the negative numbers, I should say. Only non-positive numbers are, only non-negative numbers rather, are part of this domain. And then lastly here, the functional value of 3 in function g would be the square root of 2 times 3 minus 9. That's also the square root of a negative number here, so that's going to be, again, not a real number. So take some time to do these as well. The functions listed are listed across the top here. The process is exactly the same. Take some time for that. Welcome back. Well, we've talked about before that a square root or any even root can have one solution that's rational, it can have a solution that is irrational, or it can have no solution whatsoever. And you can see that we've had an example of that in each one of these problems here. This is an example here in which the square root was rational. Here's an example here in which the answer was an irrational number. And you can see we had two examples here where the answer was no real solution whatsoever. And so let's talk about what the domain is of a square root function. What are the values that we can plug into the function that'll make it so we get a solution instead of no real solution? In this case here, we want to make sure that the radicand is non-negative. So it can't be a negative. It can be a 0 or it can be positive. So really, we can describe the domain just by taking whatever is in the radicand and saying this has to be greater than or equal to 0. That's really is the extent that we do here. Now for this one, we're going to have to figure out what that means in terms of r, but this is really as far as we need to go in order to find out what the domain is of these radical functions. This is the way we describe this in terms of interval notation here. We can have 0, or we can go from 0 all the way up to infinity, the non-negative extent here. We just can't have negative numbers involved. In the same way here, we're going to assign 2r minus 9 to a value greater than or equal to 0. And now we have to solve this inequality for what that means in terms of 9. So if we solve this for what this means in terms of r, I should say. And so when we solve this in terms of r, that means r has got to be greater than 9/2 or greater than 4.5. And so in terms of interval notation, once again, it can be as high as infinity and as low as 9/2, and it can be equal to 9/2, but it can't go any lower than that. If we plug in 9/2 into this, then 9/2 times 2 is going to be 9. 9 minus 9 is 0. The square root of 0 is fine, but we can't go any lower than that, can we? And so just take a look at these functions here as well. See if you can define what the domain of these square root functions are based upon setting things greater than or equal to 0. Take some time for that. Welcome back. Well, you might be surprised at the answer to the second problem here because it involves t being greater than or equal to some negative number, which means that there's some negative number that's okay for t to be equal to here. So it has to be greater than or equal to -2/7, which means that -1/7 would be okay for t. Yeah, because it's okay for t to be negative just as so long as this whole expression here is not negative. And if I plug in -1/7 here for t and I multiply it by 7, -1/7 times 7 is -1 plus 2 is +1. So everything is still positive inside of here, even when t can be just in this case, just a little bit negative. You can see that represented here in both of these solutions in terms of interval notation. All right, let's do the same thing here with cube roots. We're working here now with functions that involve a cube root here, and so for the first one here, f of x is equal to the cube root of x, and so f of 125 is now the cube root of 125, which is just 5. The cube root of -7, remember taking a cube root of a negative number, that's okay. But for this, we can't simplify it any longer here. The -7 or +7, neither one of those is a perfect cube. And so we'll just write it this way. For h of 10, now there's a little bit of an expression inside of the radicand here, so there's a little bit of algebra we have to do. 10 minus 5 is just 5, and so this is the cube root of 5. And lastly here, h of -3, -3 minus 5, that's -8. And -8 is in fact a perfect cube. And so the cube root of -8 is actually -2. All right, so guess what? I'm giving you 4 problems to do just like that once again here. F of x is equal to the cube root of x, and g of c here is this expression under a cube root, which involves c. Evaluate these 4 functional values here for these 2 radical functions. Take some time for that. Welcome back. Well, in particular, this first problem on this sheet might have caught you off guard a little bit here. 25 is in fact a perfect square, but it is not a perfect cube, and so you cannot simplify this at all. This is actually an irrational number here, and we can in fact think of what its value might be here. The cube root of 27 is 3, and the cube root of 8 is 2. So cube root of 8 being 2, the cube root of 27 is 3, so 8's too small, 27 is too big. It's somewhere between 2 and 3. But the rest of these should have been pretty straightforward here. You have the cube root of -1 being -1 here as well. Notice that there isn't really a problem with negative and positive radicands like we had with the square root here as well. You can have a negative radicand as so long as the order of the order of the root is odd. Okay, and I'm concerned that there might be an error on your slide here, so let's watch this fairly carefully here. But you've seen from the previous discussion on the previous slide here that it's okay to have a negative radicand when you've got a cube root or any odd root whatsoever. And so the domain of a cube root function or any odd root function is the set of all real numbers from -infinity to +infinity. And so I'm concerned here, yes, this is incorrect in fact, so we'll want to X all of that out and really give the same answer for both of these here. The answer simply is this and this. The interval here of all real numbers, and the answer here is also the interval of all real numbers from -infinity to +infinity. All right, so let's take a look here. I think, did I mess this up? I took a step back here. A major step back. Okay, here we go. So let's talk about how we graph these things here. Now, if you recall from graphing, you want to, one of the easiest ways to do it is to simply try a few points here using what's called a t-table. So in this case, what I'm going to do is try some numbers here that when I plug in for x, I get a value for f of x. First starting off with the f function here, function f being just the square root of x. If I plug in a 0 for x, I just get 0 for f of x. Okay, so that's one point here that I'm going to plot right here. And for the second one here, if I take the square root of 1, I get 1 here. So 1 comma 1 is another point here that I'm going to plot right here. Now let's start thinking in terms of what numbers can I put in here that are perfect squares. Well, the square root of 0 is 0, square root of 1 is 1. What's the number I can put in here to get 2? Hopefully you can see that that's 4. So if I put in 4, the square root of 4 is going to be 2, and so that's going to be right here. What's the next one I can put in? Well, the square root of 9 is 3. And so if I put in a 9 for x, I'm going to get 3 for f of x, and that's this point here. So as you can see, when I put all those points together and I plot the line, it looks like this. It actually looks very similar to the parabola that we had for quadratic equations here, which kind of looks like a U. This is actually a U turned on its side, believe it or not, and having its lower half shaved off. So it's just a curve. It's like half of a U here. And so you can see that that's what that looks like here. Actually, if it were the negative square roots, it would be the other half of this parabola extending now below the x-axis, but really being just a mirror image of what's on top. Let's do the same thing here with this radical function here. It's a little bit more complex, but what's the number if I, what is the number here that I get if I put in -4 here for x? Now, why did I choose -4 for this? Because -4 plus 4 is 0. I'm aiming specifically for this 0 here. So I'm noticing that I'm asking the question here, what number do I put in for x in order to get 0 as an answer here? So there's that point, -4, 0. Now I'm going to ask, what number do I put in here in order to get 1 for an answer? Now, as it turns out, that's -3. -3 plus 4 is 1. Square root of 1 is just 1. So that point is this point right here. Next one. What's the number I can put in here in order to get 2 for an answer here? Well, that would be the square root of 4. Oh, I need to set x equal to 0 for that. So 0, putting in 0, I'm going to get 2 for an answer here. If I put in 5, I'm going to get 5 plus 4, which is 9. Square root of 9 is just 3. And that's really as far as I'm going to go here. So you can see, as all those points are plotted here, that the curve now does this. Interestingly enough, let's start thinking about what happened here as we went from the square root of x to the square root of x plus 4 on the inside here. As it turns out, you can see that having this plus 4 on the inside here actually moved things to the left. That's that direction for you. So moving things to the left here in response to having a plus sign here. So you can think of this, why is that the case, that having plus 4 here moves this to the left? As we're moving from left to right here, from left to right, this gets set to 0 a little bit sooner here. It has a head start on hitting 0. This hits 0 at -4, whereas this takes a little longer. It doesn't hit 0 until 0. So at -4, when I plug this in here, I'm going to get a 0. So it comes a little early. It has a head start in going from left to right. Similarly, what do you think would happen if this were the square root of x minus 4? Well, I think perhaps you might hypothesize that it would kind of look like this. It would be shifted not to the left, but to the right. Not to the left, but to the right. So yeah, having a minus sign underneath, subtracting something from x instead of adding something to x is going to move it to the right. Now let me ask you another question here. What happens if I add something, but now it's outside of the radical? It's not inside any longer. So in this case, this would become, if I plug in 0 here, this will be the square root of 0 plus 2. That would be this right here. If I plug in 1, this is the square root of 1 plus 2, which is 3. If I plug in 4 in here, that's the square root of 4, which is 2. 2 plus 2 is 4. Interesting. Perhaps you can see here that when the number is outside the radicand, then it moves up. And I'll bet you can guess what happens if this is square root of x minus 2, with the minus 2 being outside of the radicand. That is this here. So depending upon how you situate plus, minus, inside the radicand, outside the radicand, you can move this graph up, down, left, right, whichever way that you want to do it. So, or even actually combinations of those things. You can have it diagonally up here or diagonally down here. So this is what's kind of cool about being able to graph these things and seeing how the algebra of this influences what the graph looks like. So with that in mind, take some time and graph this square root function here. Perhaps you might be able to predict even what this square root function is going to look like before even trying the t-table. So take some time for that. Welcome back. Well, maybe you were able to predict this answer even before putting together the t-table that determined that this was actually a square root function that was just moved to the left 2 spaces here, as is indicated by, as is implied or perhaps predicted by this +2 underneath the radical sign here. So you can see the points here that would manifest in this curve being plotted here, and you can see it both ways. Let's do the same thing now with some cube root functions. Here we're plotting the cube root of x, so f of x is equal to the cube root of x. Now notice with the square root function, it had a starting point and then went to the right from that point on here. Is that going to happen with the cube root function? Remember, the reason why that happened with the square root function is that you couldn't put anything negative into the radicand. Is that true for a cube root? No. So as it turns out, this thing is going to have an extent from negative infinity to positive infinity, and you're going to see that as we're plotting this here. So let's first of all try some easy stuff here. 0, 0, so that's going to be a point here. I'll plot this. Whoops. We also have 1, 1 as a possibility here as well, so I'm going to plot that. 8 and 2. Wow, I've got to jump all the way to 8 here now in order to get 2. The cube root of 8 is 2. So as it turns out, this is very, very much like the parabola we were talking about before, except it's even flatter right now. It's even less steep than the one that we were looking at for a square root. And that gets flatter and flatter and flatter as we're looking at higher and higher roots, by the way. But let's consider what happens in the other direction here, the negative direction. If I plug in a -1, I'm also going to get a -1 here. And if I plug in a -8, I'm also going to get a -2 out here. So this has a kind of almost butterfly look to it right here, where it looks on the right-hand side very, very much like our parabola, but we have sort of a mirror image of that on the opposite side here. So this extends from negative infinity to positive infinity. Let's try the same thing over here with a little bit more complex radicand. So what are some of the things that we can plug in here to make this happen here? So first I'm asking, what can I plug in to get the cube root of 0? The answer is 1. So I'm going to shade in the point 1, 0 there. 2, if I plug in 2, I'm going to get the cube root of 1. So that's going to be our value of 1 here. And if I plug in 9, 9 minus 1 is 8. Cube root of 8 is 2. So I can plug that one in here as well. So those are the positive solutions. Let's talk about the negative ones here as well. If I plug in 0 for this, 0 minus 1 is -1, and the cube root of -1 is -1. So that's here now. And lastly, if I plug in -7, -7 minus 1 is -8. Cube root of -8 is -2. So I have this point here as well. So think about how those points are going to connect together in a very similar shape to what we had over here. In fact, let's ask the question, what's the difference between these two? In going from this to this, we're seeing things move to the right, which you might be able to predict based upon the fact that we have an x minus 1 up here. When there's a constant up here, that causes things to move to the right. We saw that with the square roots, and it's also true for the cube roots here. Okay, so try this one yourself here. Find the graph of the cube root of x minus 3. Take some time for that. Welcome back. Well, the algebra of figuring this out might be a little bit challenging, but in this case we were all just working towards the same thing here, making it so that cube root would give us a nice even 0, 1, 2, -1, or -2 here. In this case we found that when we plugged in 3 minus 3, we got the cube root of 0, which is 0. We plugged in 4, 4 minus 3 is 1, the cube root of 1 is just 1. 11 minus 3 is 8, the cube root of 8 is 2. 2 minus 3 is -1. The cube root of -1 is -1. And -5 minus 3 is -8. Cube root of -8 is -2. And so when we plot this, we see the same cube root shape here, but now being shifted to the right 3 spaces. But you already knew that was going to happen, didn't you? When you took a look at this radicand up here, x minus 3, you knew that that was probably going to be the case, in which this thing gets moved to the right 3 spaces. Well, what an hour and 20 minutes it's been here. We have covered principal square roots, negative square roots. We've covered some vocabulary when it comes to radicands. We have talked about how when it's a square root, you can either have a rational solution, an irrational solution, or no real solution whatsoever. We talked about how that's true actually for all even roots that you work with. 4th roots, 6th roots, 8th roots. And so whenever we're working with a function that involves an even root, like a square root or a 4th root or a 6th root, we always have to take a look, be careful when we're assigning the domain of that function. The radicand has to be non-negative. It can be either 0 or positive. We also talked about cube roots as well as other odd roots there, in which case the radicand doesn't have to be non-negative. It can be positive or negative. And so when we're considering the domain of an odd root, we don't have to worry so much about whether or not it's positive or negative. Positive or negative values can work either way. We then talked about, actually, let me list it up here. We talked about principal and negative roots here. We talked about calculating higher roots. And we also talked about simplifying some expressions here involving n and n. And do they fully cancel out? When it's odd, when it's an odd number here, yeah, n and the exponent n, the root of n, they'll cancel each other out. But if it's even, then the result here becomes the absolute value of a. Remember that? When we talked about the domains of square and cube root functions, we have to make sure the radicand is positive for square root functions. We don't have to worry about that with cube root functions. And lastly, we did some graphing, didn't we? We brought back that process of creating that t-table. We graphed square root and cube root functions, and we even explored a little bit how those things will shift in response to how the algebraic expression inside and outside the radicand can change. Well, this is pretty significant stuff here, so I would encourage you to go through the activity sheet that accompanies this and just make sure that you follow each one of those concepts that was being described here. There's a lot that was being discussed, there's a lot to cover, and there's a lot on the homework assignment that you have to do alongside of this. So take care, we'll see you soon, and I'll see you in class.